Okay, we are going to look at a topic, as you can see, entitled Improper Integrals. Before I explain what those are, I want to review a little bit about, of all things, finding limits, because we're going to be looking at a limit process when we talk about improper integrals. And so I just wanted to review a little bit, in particular, some limits at infinity. And I've given you the graphs of three common functions, just to help you remember what those look like. In particular, don't forget this inverse tangent or arctangent function has horizontal asymptotes, if you remember. This one is y equal pi halves, and this is y equal negative pi halves. Okay. When we look at limits at infinity in particular, if c is any constant and r is a positive constant, then the limit as x goes to infinity of any constant is going to be c, right, the constant itself. If you graph a constant function, it's nothing more than a horizontal line, so the value of the function does not change as x goes to infinity. It stays at c, and so the limit is equal to c. In this next example, right, this is a very important one that we use a lot. As x goes to infinity, right, what's going to happen? C is a constant, it stays fixed, but the denominator has the variable, and notice it's to the r power. Since r is positive, x to the r is going to increase as x goes to infinity. It's going to get bigger and bigger, and so as the denominator gets bigger and bigger, this overall fraction is going to do what? It's going to get closer and closer to zero. In fact, that's what the limit is. It's an important one that we've actually used that when we were looking at the very beginning of the course, when we looked at those right hand and left hand sums and then took the limit as n went to infinity. Very similar to that. All right, we've got the graph of e to the x above. What's the limit as x goes to infinity of e to the x? What's happening to the graph as x gets larger and larger? Well, it's increasing without bound. It's going to infinity. What's happening as x goes to negative infinity for e to the x? Well, what's happening here? Well, if you remember, y equals 0 is a horizontal asymptote for the graph of y equals e to the x. And so e to the x is going to 0 as x goes to negative infinity. What about as x goes to infinity of e to the negative x? You should think about, what does the graph of e to the negative x look like? Okay. A couple ways you can think about that. I've replaced x with negative x. Does everyone know what happens when I replace x with negative x to the graph? It's going to be a reflection in the y-axis. So if I do a reflection in the y-axis, then I can graph y equal e to the negative x. Or another way of thinking about it, of course, e to the negative x is just 1 divided by e to the x. And if e to the x is going to infinity as x goes to infinity, 1 over e to the x is going to 0 as x goes to infinity. So a couple ways of thinking about that. Look at the natural log function. As x goes to infinity, what's our limit here? As x goes to infinity, this function also is going to infinity. Certainly not as rapidly as e to the x, but still, nonetheless, it is approaching infinity. It's becoming unbounded, if you will. Keep in mind, as x approaches 0 from the positive side here, we have a vertical asymptote of x equals 0 for the natural log function. And as we approach 0, where are we going? We are dropping down, right? The values are becoming unbounded in this direction, and so we are approaching minus infinity. What about the limit as x approaches infinity of sine of x? I didn't graph that function up there, but I hope you remember what it looks like, right? Sine function's going up and down between 1 and negative 1 forever. As x goes to infinity, are we ever going to settle down to any one value? Clearly not. So in this case, the limit actually does not even exist. Right? We're not going to settle down to any value. We're not approaching 0, 1, or negative 1, or any value in between. We just keep bouncing back and forth forever between 1 and negative 1. And then I include the graph of the arctangent function here to help. What's the limit as x goes to infinity of the arctangent function? As x goes to infinity, we're approaching pi over 2. And as x goes to minus infinity, where are we going? We're approaching the other horizontal asymptote of y equal negative pi over 2. So this is just a review. We've already looked at some of these limits before, just reminding you of those. You'll need to know these as well as the limits of the behaviors of the other functions that we encounter. Another thing that we might encounter from time to time in this, just to let you remember hopefully about that, and that is Lhopitals Rule. If you remember Lhopitals Rule from Calculus 1, how we apply that if I have a limit of a ratio of functions that is either of the form 0 over 0 or infinity over infinity, then the limit as x goes to plus or minus infinity of this ratio is equal to the limit of the ratio of the derivatives of those two functions. Right? This is not the quotient rule we're applying here, but it is known as Lhopitals Rule. And we have several indeterminate forms that we can look at. These are all indeterminate forms here, if you remember from Lhopitals Rule. The only ones, though, that we can use Lhopitals Rule for are 0 over 0, infinity over infinity. Okay, with that introduction, I want to take a look at improper integrals. And there are two types. And they're called improper because they basically don't fit the proper, if you will, definition for applying the fundamental theorem of calculus part 1, the evaluation theorem. First of all, the integral requires the interval to be over a finite interval. From a to b, the lower limit is a, the upper limit is b. Those are finite quantities. And also, it requires the integrand that we're integrating to be a continuous function over the interval. Now, we can integrate some discontinuous functions, but not ones with infinite discontinuities or vertical asymptotes, as we'll see here. So integrals that have infinite intervals of integration, you might say, where would you have an infinite interval of integration? Well, it turns out there's lots of application for that in probability theory, models that are used to calculate probabilities of events occurring, and other such applications. But we're going to look at integrals with an infinite limit of integration. And then integrals that have an integrand that has an infinite discontinuity or vertical asymptote. So these are what we call improper integrals. Now, with improper integrals, we're going to first look at the ones with infinite intervals of integration. It's going to be pretty easy because when you look at it, you're going to have an infinity symbol, either going to positive infinity or from negative infinity up to some value. So the a and b in this case are going to be real numbers. So if the function is continuous for x greater than a, then this integral, a to infinity, is an improper integral. Now, what do we mean by this? Well, this is what we mean, and here's where the limit comes in. Right? This is the limit as t goes to infinity of the integral from a to t f of x dx, provided the limit exists. So what's exactly going on here? First of all, notice the limit, the integration variable is x. So I want to be careful when I use this variable here. I chose t. It can't be x. You have to choose something other than x. X is used for the integration variable. So use a different variable. I'm using t here. You can use other variables as well. Okay. But what's basically going on here is we have the graph of some function, and let's say here's the value of a, and I can look at maybe the graph of the function looks like this. And so when I say the interval is from a to infinity, and we have our left endpoint here is a, where's our right endpoint? Well, there is not one, right? It just goes on forever. So we're looking at this area, and someone might be saying, well, isn't that an infinite area? Isn't that region go on forever? yeah, the boundary for this area is going to be infinite. The perimeter is infinite, but it turns out that the enclosed area can be finite. Now, that shouldn't be too surprising. There are many examples in mathematics where that's true, and we're going to be looking at this quite extensively in Chapter 10 with infinite series. But just think about, for instance, the number 1/3. That's a finite quantity, 1/3. Right? However, you can think of 1/3 as an infinite sum. Right? 1/3 is 0.3333 forever. Well, that's equal to 0.3 plus 0.03 plus 0.003, etc. Right? There's an example of an infinite number of things that add up to a finite quantity. So if I break this up, look at the rectangles, if we're doing rectangles to approximate the area, and then push the limit to infinity, it could be we find out that this area is actually finite. Now the idea behind finding this area is this: instead of going from a to infinity, I can't use the fundamental theorem of calculus on that, but I choose some value of t, right? This value of t is going to be greater than a, so right to here. And now from a to t, whatever t is, I can find that area, right? That area I'll shade in. That's certainly something we can find with the fundamental theorem of calculus, right? So I can find this area. And then what do? Well, now then what do? We push t to what? We push t to infinity. We push t to infinity. As t goes to infinity, what's this red area approaching? If the limit exists, it is equal to the area that we are looking for in the original integram, the area under the curve. Now I drew the function as being positive above the x-axis. This would still apply even if the function were below the x-axis. If we have, for a value of x less than b, the function f being continuous, and we're going from negative infinity to b, this improper integral is interpreted this way. Limit as t goes to negative infinity, notice that t is down here, right, to b, and then provided this limit exists. So the idea is we're going to evaluate the integral from t to b, which is going to be a finite interval, and we can use the fundamental theorem of calculus for that. We'll get an expression in terms of t, and then we'll take the limit as t goes to negative infinity. If one of the limits above exists, we say the improper integral converges. If the limit does not exist or is infinite, we say the improper integral diverges. Now, these are situations where we have just one of the two limits are infinite. What if they're both infinite? Negative infinity to infinity, integrating over all real numbers. Well, here we can pick any real number, I'm calling that a, and split it up into two different integrals. See how that's going to work? All right, notice this a and this a. So this will be everything less than a, this will be everything greater than a, and we add them up together. Well, in order for this integral to be convergent, both of these integrals have to converge. Right? Both limits would have to exist. If one or both of these integrals diverges, then this integral diverges. And we'll see one example of this towards the end. All right, let's take a look at some examples then. We'll start off with some simple ones and work our way up. Here we have the function 1 over x squared. This is the graph of x squared. And here, if I just sort of visualize what's going on, x equal 1 to infinity, this is the graph again of 1 over x squared. Then, we're talking about this area here forever. It keeps going, right? But notice 1 over x squared gets close to the x-axis very rapidly. Very rapidly. So let's see what this looks like, right? So I am going to emphasize that this must be written in this way. In other words, you have to write as the limit as t goes to infinity, the integral from 1 to t. And I'm going to write 1 over x squared as what? X to the negative 2. Okay. And now, I've got the limit out here, but, this right here is an integral I can do because t is a finite number. We're thinking of some value greater than 1. Right, so t will be, some value over here, and I can just integrate from 1 to t. I can find that area. So what's the expression for that? Well, we can do that. I still have this limit, and we'll take care of that in a minute. What's the antiderivative of x to the negative 2? Add 1 to negative 2 and divide by that, right? By the power rule. It's just the power rule. What are our limits? Evaluate at t, the upper limit, and then at 1. Okay. This simplifies down what? X to the negative 1 is 1 over x. So that's negative 1 divided by x. And so this is the limit as t goes to infinity. And when I plug in t, what do I get? Negative 1 over t. And then minus a negative what? 1 divided by 1? A negative 1. Minus a negative 1. Of course, it becomes plus 1 here. Okay. But now, so for any value of t, I can find the area under this curve from 1 to t, right? It's going to be basically negative 1 over t. Of course, this will be plus 1, or 1 minus 1 over t. And so you can see what's happening as t gets bigger and bigger. What's happening? We can now take the limit as t goes to infinity. What happens to this expression here? As t goes to infinity, that's going to go to 0. Right? And so our limit is 0 minus a negative 1, or positive 1. Right? The limit exists, right, as a finite number. So what do we say? We say the integral, the improper integral, converges. And we say its value, I guess there's no apostrophe there, its value is 1. That's the value of the integral. Okay. Now, I do want you to show this correctly. So do not do the following. Do not do the following. Let's rewrite this as x to the negative 2, 1 over x. So suppose this again is the same integral from 1 to infinity. Do not do this. The antiderivative of x to the negative 2 is negative 1 over x, and say 1 to infinity this way, and do this. Do not do this. This is incorrect and will cost you points. So don't do that. Right? You cannot use the fundamental theorem of calculus if there's an infinite limit of integration. And what's going on here? Infinity is not a number. You can't plug in infinity. Right? You can take the limit as t goes to infinity of 1 over t, and that expression is going to 0. Okay. So I do want you to do the correct notation here. The correct notation. Okay, let's look at another example. Very similar to the one we just did. Instead of 1 over x squared, we're going to do 1 divided by x. So again here, I'm going to take the limit as t goes to infinity, 1 to t. I'm going to leave it as 1 over x this time, because what's the antiderivative of 1 over x? What's the antiderivative of 1 over x? Would I use the power rule on that, right? That is x to the negative 1? No. We should recognize that as being the antiderivative of 1 over x being the natural log of the absolute value of x, right? The absolute value of x. However, I'm just going to write natural log of x. How can I get away with that? Look at my limits of integration from 1 to t, where t is some value greater than 1. And so we can evaluate this now. We take the limit as t goes to infinity of natural log of t, right, evaluate this at t, minus the natural log of 1. Now the natural log of 1 I know is equal to 0. This is equal to 0. But what's happening then, so I get the limit as t goes to infinity of the natural log of t. And what did we say about that limit? Initially, remember we looked at the limit of the function natural log of t as t went to infinity. That goes to infinity. Right? this tells me that the integral diverges. Now, I want you to take a look at this situation here. So this is the graph, right, that we did. So this integral 1 over x from 1 to infinity diverges. The integral from 1 to infinity of 1 over x squared converged, remember, and its value was 1. So let's take a look at this. Here's the graph of 1 over x squared. What would the graph of 1 over x look like? Well, we can do it. When I plug in 1, the output is 1. When I plug in 2, 1 over 2 is a half. When I plug in 3, I get 1/3. When I plug, I get 1/4. The graph of 1 over x is getting closer and closer to the x-axis, just like 1 over x squared. But it's always going to be a little bit above that graph for values greater than 1. Okay, so let's think about this now. This shaded in area that I have here under the curve 1 over x squared, that area is finite. In fact, the area that I've shaded in is exactly equal to 1. Isn't that amazing? The total area that I've shaded in is exactly equal to 1. Even though this perimeter, right, is infinite, because how far do I go down this way? Forever. Right? It goes forever. Follow this curve forever. Right? The perimeter distance around is infinite. But the shaded in area is actually finite. Okay? That may be disturbing for you, but that is the case. And again, I gave you the example of the number 1/3, which can be thought of as a finite number, yet it's made up of an infinite number of things that we're adding together. So very similar, we have a case where we have a geometric region that's finite in area but infinite in perimeter. But here's an interesting thing. Now if I were to look at the area under the graph of 1 over x, right, which I would include this shaded in area plus this area in between here, this area in between the two graphs would be included. If I shade all that area in, what is that equal to? Is that finite? Answer, no, it's not. It's infinite. Right? That's what happened when we write the integral diverges. The area is unbounded. So interestingly enough, this little strip of area here, if I go all the way out, is actually going to be infinite. That area just in between these two curves is actually going to be infinite, because we already know this blue shaded in region was finite, was only equal to 1 square unit. If everything under the green curve is infinite, that would mean that this little strip here, which goes on forever, is infinite. Maybe a little mind-boggling, a little bit strange. But that's what sometimes happens, especially when we begin to look at this infinite process, this going to infinity. Okay, let's take a look at a couple more examples. Actually, yeah, let's look at this and then 2 more, and then we'll take a break. Yeah, maybe I'll stop here and we'll do a second video after this one. I want to look in general. We looked at 1 over x squared and 1 over x. I want to look at this where p is any real number here. So we already did p equal 1 and p equal 2. So let's suppose p is not equal to 1, because we've already got, p equal 1 case was right here. We already did that, it diverged. P equal 2 case, it converged. Right? So let's take a look at this in general. So the limit as t goes to infinity, integral from 1 to t. I'm going to write this as x to the negative p. Right? That's what 1 over x to the p is, right? X to the negative p. And so now this integral we can do, finite limits of integration. And what's the antiderivative? It is negative p plus 1 divided by negative p plus 1. Right? I mean, that's just the power rule. And we're going from 1 to t. I want to clean this up a little bit. The limit as t approaches infinity, before I evaluate x to the negative p plus 1, is that the same as x to the 1 minus p? Yeah. Negative p plus 1, 1 minus p. So let's just do it that way. And now let's evaluate this. At t, I replace x with t. And let me pull the 1 over 1 minus p out. 1 over 1 minus p. Let me factor that out. And I'm going to left with t to the 1 minus p minus 1 to the 1 minus p. What is 1 to any power? It's 1, right? So we just get 1 there. So I've factored out the 1 over 1 minus p out. So the only thing that's changing as t goes to infinity is this thing. It's this thing. Okay? So let's take a look at that. The limit as t goes to infinity of t to the 1 minus p. Let's just take a look at that on the side here. Okay. Well, that's the same as the limit as t goes to infinity of 1 over t to the negative quantity 1 minus p, or negative 1 plus p. Negative 1 plus p is the same as p minus 1. Right? And so, all right, I can look at it this way because we've talked about this already. This thing I know is going to be equal to 0 if what? If this exponent is positive, right? So if p minus 1 is greater than 0, or if p is greater than 1. So, go back up here. What's going to happen? If p is greater than 1, then this thing is going to go to 0, right? This thing is going to go to 0, and we're just left with a negative 1 here. All right, 0 minus 1 times that. What happens if p is greater than or equal to 1? Well, if p is greater than or equal to 1, then this exponent here is going to be greater than, less than or equal to 0. Right, if p is going to be less than or equal to 1, p is less than or equal to 1, then this exponent is negative. And what's going to happen, this 1 over t to a negative number is going to flip up, and that limit is going to go to infinity. It's going to go to infinity. Right. And so this whole thing is going to infinity. Infinity minus 1 is still infinity. All right, p again is a constant here. So this thing is going to infinity if p is less than 1. Technically, I guess if it's less than 1. Let's do it this way. It's infinity if p is less than 1. If p is equal to 1, p minus 1 minus 1 is 0. T to the 0 power would be 1. Now we just have 1. This thing would be technically going to 0, I guess, in that case. If for some reason that seems strange to me, this should be infinity if p is equal to 1 as well. P is equal to 1. 1 minus 1 is 0. T to the 0 power is 1. Oh. Never mind. We already covered that case. I'm being stupid. P is not equal to 1, so... okay. What happens when P equals 1? We've already figured that out. It's infinity. I'm sorry. Sorry for my ignorance here, but when P is equal to 1, we've already covered that. So yeah, this is true if P is less than or equal to 1. Sorry. I forgot that we said P is not 1. Okay. But we know it's infinity if it's equal to 1 because we did it up here. Right? We did it up here. But again, if p is greater than 1, then this goes to 0, and so we're 0 minus 1. It's negative 1 over 1 minus p, or if you swap the signs down here, 1 divided by p minus 1 is the same thing as that. And that's true if p is greater than 1. And so what happens is we get this, it turns out, in general. The integrals of this form are what we call p integrals. They are going to converge if p is greater than 1. Okay. Now this has a little bit of a, it has a here instead of what we had up here, which was 1. We started at 1. But you can start at any value a. If you plug in 1 here, you're going to get 1 to any power. The top will be 1. And you get 1 over p minus 1, which is exactly what we had if p is greater than 1. And then it diverges otherwise, right? Because the limit is going to be infinity if p is less than or equal to 1. And so this is a nice thing to remember, and we're going to use these p integrals later on in the course, and so it's a good thing to remember this. In fact, we can quickly do some integrals now just by looking at the value of p. Okay, remember, it's 1 over x to the p. If p is greater than 1, it's going to converge. If p is less than or equal to 1, it's going to diverge. So let's take a look at a couple of cases. What's the value of p in this case? 0.7, right? Which is indeed less than or equal to 1, so this diverges. What's the value of p here? It's pi, right? Pi is greater than 1, right? Pi is 3.14, so it's going to converge, right? This converges. And in fact, we can even find the value. What's the value of this? If we were to take the limit and do all the work, what would we get, right? We already know. It's a to the 1 minus p. A is 3, so it's 3 to the 1 minus p, which is pi, over p minus 1, pi minus 1. Okay, you can use your calculator to approximate it, but that's the value of it. It converges. What's the value of p here? Square root. What in the world's going on there? Oh yeah, x to the what? 1/2 power. P is 1/2. Right? But 1/2 is again less than or equal to 1. So this diverges. What's the value of p here? Is it negative 6? Is that what it is? No, be careful, it's not negative 6. X to the negative 6 is 1 divided by x to the 6. The p is 1 over x to the p. It's got to be in that form. Okay, so the p is actually 6. And therefore this converges. Okay, so if we just need to know whether a improper integral converges or diverges, and it is a p series, p integral, excuse me, then we can do this. But a lot of improper integrals are not necessarily p integrals, and so we can't always use this shortcut. Okay, we're going to stop the video here, and then we're going to look at, in the next video, some more examples.